but it's very nice to see you. My pleasure. Sorry.
Okay, so it's a great honor for me to be here. And I don't have any amusing stories to tell about Maurício. So I'm sorry. Anyway, I find him an inspiration, not only because he is a great mathematician, but he's a great guy, so thank you. All right, so I'm going to be talking about things I've worked on for a number of years, and I'm not going to follow Etienne's advice, and I'm not going to give any proofs in this talk. I'm sorry. So the aim of the talk is to present, to explain what pruning is, and so pruning, very roughly speaking, is a way of describing the topology of the dynamics in the Henon, say, family, or more generally in families of two-dimensional homeomorphisms or diffeomorphisms. And so I'm going to be sort of saying what pruning is in a few different ways. And then I'm going to talk about some recent results that Valentin Mendoza proved about proving some special cases of this so-called pruning front conjecture. And I'll say some other things as well. So to start with, what is pruning, right? So the pruning idea was introduced by Cvitanovich in the 80s, I suppose. And the idea, as I just said, was to be able to describe the topological dynamics in families. Okay? So you have a family of homeomorphisms or diffeomorphisms of the plane or of the surface in general. I mean, he was especially interested in the Henon and the Losey family. And you want to be able to describe what is the topological dynamics. What are the periodic orbits, how you describe them, how do you find them, and the main observation of Cvitanovich's, which I hope to show here in a second, is an observation, meaning that you observe something, and what you observe is you just look at the Henon family, you make the parameters vary, and then you see things. And what do you see? What do you see is that, well, if you draw the right thing, so if you draw stable and unstable manifolds, what you see as you vary the parameter, and you'll see it here too, is that these things uncross. So let me show. So this is my first Beamer talk, and I'm even going to show a program. The Beamer I did, but the program is well beyond my capability. So this is Toby. So here is an example. So this is what is drawn here: the stable and unstable manifolds of a couple of fixed points of a Henon map. And here's what you see when you look at these things. So the Henon family so there are two parameters A and B. So say fixed parameter B, they're on top of the screen there, but in any case, so fix the parameter B and move A. So that's what I'm doing here. I'm going to move that cross there to the left. And what you see with these stable and unstable manifolds is that they move. And at some point they touch, and you keep moving, and they start uncrossing. Right? So that's what you see, and they uncross, and then uncross, and then go on, and eventually it disappears. Right? So that's what you see. And then you decide to say, well, so that's what it's what you see, it's what happens. And so what Cvitanovich proposed is that, well, anyhow, so let's describe this mathematically, right? So first observation is this: is when the parameter is very large, the parameter A is all the way to at that point there. What you have are the stable and unstable manifolds of a horseshoe. That's a hyperbolic horseshoe. You can prove that this is a hyperbolic horseshoe. There's a full two-sided, two shifts worth of orbits. And where are they? Well, they are exactly at the intersection points of these stable and unstable manifolds. So that's what describing the dynamics is in this case. You say that the non-wandering points are exactly the closure of the intersections of these stable and unstable manifolds. And how do you describe these? Well, this Melo kind of did that. You describe them by a subshift of finite, well, a subshift of finite type, not even that. This two-sided two-shift, the full two-sided two-shift. So that describes those. And as you move the parameter, well, what happens? These things uncross, so you lose parts of that. So you describe, so Zvitanovic's idea was to say, well, okay, so Henon maps can be described as partially formed horseshoes. Okay, so that was Zvitanovic's idea. And then he proposed, well, right, so clear though these pictures may be, it's not very easy to make this very precise, make this mathematically precise. Okay, so and it's even less easy to prove anything about it. So what I'm going to do for the first half of the talk, I suppose, or for most of the talk, is to explain ways of kind of making this mathematically precise. Okay? So the rough statement that these are partially formed horseshoes is that every map in the Henon family, say, what I showed here was the Henon family, but if you could draw similar pictures for the Losey family, is that they are partially formed horseshoes, as I said, and that is, they are full horseshoes from which you've taken away parts, okay, some parts. So it's a full horseshoe from which parts of dynamics was destroyed or pruned away. Okay, so you prune a tree, you prune the dynamics of the horseshoe. Okay, so that's the rough statement, but how do you make this mathematically more precise? Well, anyway, so there are several subtle things about this, but one of the subtleties that makes it, kind of drives the point home that you should be careful is that there's this result of anti-monotonicity, which shows that at near every one of those tangencies that we saw here, periodic orbits or even intersections, actually. So at near every tangency, intersections are being destroyed. That's what we saw. But they're also being created at every moment. Right? So these intersections that you saw here very clearly disappearing, there's a theorem that proves that, well, they disappear, but they also appear elsewhere all the time. Right? So then, you have to watch out. Right? So if you're going to say that things are partially formed horseshoes, you have to, to be aware of these things. And so as I said, tangencies or crossings are disappearing and reappearing. And then, but anyhow, at every given moment when things are disappearing and then or reappearing, maybe they are reappearing in a way that they were already there before. That's what being a partially formed horseshoe is all about, right? I mean, they disappear and then they reappear and then they disappear and then they reappear. But then you have to know what it is that you're talking about to be able to say that something that appears now was there in the full horseshoe to start with. Okay? So anyway, so the first version, mathematically precise version of what this was all about was I did in my thesis, and what I did there was to construct by sort of hand, so to speak, models which were like this. You start with the horseshoe, the full horseshoe, and then you carefully construct these regions on which you can destroy the dynamics by anisotropy. Right? So So there are these regions that I don't want to talk about the technicalities involved, but then what I did there was you construct these regions called pruning regions, and then for this type of regions you can actually construct an isotopy which destroys all of the dynamics inside of the pruning region and leaves everything outside of the pruning region untouched. Okay? What am I calling a pruning? I'm not saying. Well, so I'm not, this is not the, I mean, you know. This is not, these are not the pruning fronts of Stefanovic, but anyhow, so if you have a horseshoe, there are some regions, some pieces of the horseshoe, where you can define an isotopy that in the saturation of this, you have to make this invariant by the dynamics. And then there's some open set here. And you build an isotopy which is supported on the open set. It erases all the crossings. So there are lots of crossings all over the place here. There's a lot of dynamics inside of here. And then you construct an isotopy that destroys all this dynamics and leaves everything outside exactly as it was in the horseshoe to start with. And then anyhow, so that produces a map, that's a model, right? And then you do this in all possible ways. So for every one of these pruning regions, you construct one of these isotopies and that you've produced a map, which is a model, right? And then you consider all the models that you construct in this way, and you call it the pruning family. It's just this family of models that you construct by hand. Right? And so that's called the pruning family. So the pruning family is made up of all the maps that you start with the horseshoe, which I'm calling. So F is is the horseshoe now, and then the pruning family P of F is the set of all maps obtained by these pruning isotopies. That is, you build one of these regions that I'm not explaining very clearly what they are, but in any case. So there's an open set where you can construct an isotopy, and then the map F sub P is what the map you obtain at the end of the isotopy after killing all of the dynamics inside the pruning region. Right? And then you put all of these in a bag and you call that the pruning family, right? For the horseshoe. So the first way to, the first version of the pruning front conjecture is this model version that up to semi-conjugacy, the Henon, so H and L there stands for Henon and Losey. So up to semi-conjugacy, the Henon and Losey families are contained in this pruning family, right? So so here we've constructed this family of models, and one way of formalizing this pruning front conjecture of Stefanovic is to say that you've constructed enough models to model all maps in the Henon family. Okay, so that's the first version of the pruning front conjecture. And then these words up to semi-conjugacy are there to avoid some silly, things that might happen, right? So you say up to semi-conjugacy, and then you can be more specific than that. You can say that you can specify what kind of semi-conjugacies you want. I mean, one of them is called a zero entropy semi-conjugacy, which zero entropy equivalence. Anyway, but you can construct your own. Okay?
So when you say H, the semi-conjugacy, which direction?
But in fact, you may have to do it in both directions. Yeah. So, well, you may have to. Right, so. All right. So that was the first version of the first way to mathematify or to make mathematically precise this description of the Henon family. So there's a second way, which is to introduce these so-called pruning parameters. Right? So I'm going to introduce here the motion of a set to be. This is the name is inspired by holomorphic motions, but I want this motion here to be not a holomorphic motion in that I'm not requiring the motion to stay injective all the time. So a motion of a set, so you take a set in R2, say, a motion parametrized by a connected set lambda with a base point lambda naught is a continuous map from the parameter set together with the set A that you're moving into R2, such that at the base point you have the inclusion. Okay? And then it's a continuous map, and then you're just moving the set, right? And in particular, points could be colliding, and things could be happening. Okay? So then we denote, phi is the motion, right? Phi lambda is the motion at any given moment of the moving, and A lambda is the set after you moved it lambda forward or whatever. So you can find a pruning parameter to be the following thing. So you start with a family parameterized by your connected set lambda. And here, of course, what I have in mind is the Hanon family parameterized by these parameters A and B or whatever else. But in any case, you could think of F lambda as the Hanon family or the Losey family. Is a continuous family, a homeomorphism of R2. So a parameter lambda 1 is a pruning parameter with respect to the base parameter lambda naught if the following two conditions hold. So first there is a subset A of R2, a connected subset of the parameterizing set with these two parameters in there, and a motion. So you move this set A so that along the motion you have semi-conjugacies, and then the second condition is that at the end the whole non-wandering set of the map F lambda 1 is your moved set A lambda 1. Right? So you have a subset, so let me repeat this. So you have at the base parameter you have a set A. So where is that? So there's a subset A of R2, and you identify it as at the base parameter, and then you move the set, and at the end of this motion, what you have is the whole non-wandering set of your map. Okay? So that is what a pruning parameter is, and then the second version of the pruning front conjecture is to say that. So again, right, the Hanon and Losey families are parameterized by all of R2, and a second version of the pruning front conjecture would be to say that, well, so both families have R horseshoes for the parameter A large enough, and to say that, the second version of the pruning front conjecture is to say that every other parameter is a pruning parameter. In other words, for the Hanon and Losey family, you can always find a subset of the horseshoe, that is a subset of the two shift and two symbols, that you can move. Perhaps some points will collide along this motion, etc. But at the end of this motion, what you have describes the non-wandering set of any Hanon or Losey map. Okay? So that's the second version of the second way of formalizing this idea that, Hanon maps are partially formed horseshoe. You moved a piece of the a sub-piece of the non-wandering set of the horseshoe till you describe any map in the Hanon family. Okay, so that's version number 2. And then there's a third way of formalizing this, which gets to be more combinatorial. And I have to introduce the concept of braid types for that. So let me say what a braid type is. So an isotopy, So an isotopy is said to be relative to a subset A if the points of A stay put along the isotopy. So stay put meaning that along the isotopy, the point X goes exactly as it goes at instant 0, right? So you have an isotopy which is some family of maps, and the point an isotopy is relative to a set A if it does to the point X so what it does to the point X does not change along the isotopy. Okay, so that's what to be relative is. So, and given a surface homeomorphism F, and F again is meant to remind you of the horseshoe, say, a set, and a finite, not finite actually, any invariant set A the braid type of A is the isotopy class of F relative to A, right, up to topological changes of coordinates. So what is the braid type of an invariant set A? You just put your fingers on the set A, and you let the map vary outside of A by an isotopy. That's it. Okay? So in this set A might be anything you want. It might be a periodic orbit, it might be an invariant Cantor set, it might be all of the non-wandering set, whatever. Right? I mean, okay, so that's the braid type, but you only record what happens at this set. I mean, the rest can be varied in a family, right? So, but your set, you put your fingers there and they have to stay. Okay? So here's another way to say it. So if you have two homeomorphisms of the same surface, you say that the braid types of an invariant set for G and an invariant set for A are the same if there is a homeomorphism, a change of coordinates in the surface that takes one set to the other and which conjugates the two sets in the complement, or it doesn't quite conjugate in the complement, but it conjugates something to its isotopic. It conjugates G to something which is isotopic to F. Okay? Why? And the isotopy, of course, is supposed to keep A fixed. Okay, so here's the third and fourth versions of the Pruning Fringe conjecture, this braid type version. So it's to say that all Henon and Losey braid types are horseshoe braid types. Okay? So you identify so that's what I was talking about in the beginning. If you know what you're talking about when you're going to talk about things appearing, disappearing, and then reappearing, you have to know what it is that reappears. And how do you identify some crossing that was there before and then ceased to exist and then happened again? I mean, how do you know that a crossing is this or that, right? And so this is a way of doing it. I mean, so you say that the braid type, well, you specify that a type of crossing or a type of orbit or a type of invariant set, and then you say that all Henon braid types are horseshoe braid types. That is, if you take any invariant set in a Henon or a Losey map, there is an invariant set of the horseshoe with the same braid type. Okay? So that's the third version. And then we can weaken that a little bit. So I'm talking here about any braid types, Cantor sets, you name it. What? So these are all conjectures. Oh, absolutely not. No. That's very far from being proved, as far as I know. Yeah. And so even... So you could be less demanding and say that no, I'm not going to look at braid types of big Cantor sets and this, that, and the other. I'm just going to talk about finite invariant sets, and I could even be more kind of specific. I'm going to only talk about periodic orbits. Okay, so I'm only going to look at the periodic orbits of the Henon map, look at their braid types, and say, aha, can I find one in the horseshoe which is just like that one? And even that is not known whether all Henon braid types of periodic orbit braid types are in the horseshoe. Okay? So, well, sounds simple enough, right? I mean, look at your favorite Henon map, pick a couple of braids, a couple of periodic orbits, understand their braid types, and compare it with the horseshoe. Can you do that? And I've done this many times. I've never found anything that's not of horseshoe type. But then again. Okay, and then there's the weakest possible version of so the weakest possible version. I'll get to it, but roughly speaking, what we talked about was decreasing in sort of intensity as we went on. So the first version constructed explicit models for the dynamics, right? So you say, so I take the horseshoe, I take a region that I know what to do with it, and then I go there and I construct an isotopy. At the end of the isotopy, I have a model, and I say, aha, I have here this model, I understand it, right? And then I put all the models in a bag, and I say, here's my bag of models. You present me a Henon map, and I come up with a model for my bag. That's quite specific. So this The second version, I was being less kind of demanding perhaps, and I was talking only about the non-wandering set, and I said, well, I can actually take a subset of the horseshoe, I can move it, and then that is the non-wandering set of your Henon map. And that's a little less demanding. And then, so the third version we saw is that, well, no, I'm not going to, I'm going to identify the type. Okay, so the type of a horseshoe orbit is this. I specify it via these braids, and then I say that, well, okay, so you come up with your Henon map, you pick one orbit there or one invariant set, you give it to me, and I come up with one in the horseshoe that had the same type. Okay, so this is kind of getting weaker and weaker, and so you could. So, and all of this is very determined by the two-dimensionality of things, right? I mean, so the isotopies, everything here had to be on the plane, right, or on the surface or something. So, and then you could say, okay, so I'll kick the bucket, as we say here, and I'll just forget about dimension 2, and then say, okay, forget it, okay? So, is it true that it's possible to describe the Henon family or maps in the Henon family as subshifts of the two-shift? So, can you always describe the non-wandering set or of any map in the Henon family as a subshift? Any old subshift, not necessarily, right? So that is the weakest possible rendition, so to speak, of this. And even, well, that we don't, I mean, in general, that's not known, that I know of. Anyway. So what is known? Okay. So one thing that is known is this: is that if you start with, so the Henon family is got this formula. And this formula here, if you make b equal to 0, is a minus x squared. And a minus x squared is this famous, very intensively studied family of one-dimensional maps that people know lots about. And if b is small, the Henon map is a small perturbation of the unimodal family. Right? And so if you start with a unimodal parameter, the A parameter hyperbolic, that is, if you make the unimodal map hyperbolic, and you perturb it a little bit, adding B very small, then the map you get is essentially the unimodal map, is a hyperbolic perturbation of a unimodal map. The unimodal map, you know what it is, and then you can prove the pruning from conjecture for these maps. Okay? So for those maps, it's known that there's, in fact, you can prove the strongest possible version. Okay, so there's a model. You know exactly what the pruning region is for that, and you can describe everything explicitly. So that is, well, that's nice, but it's well known that is very much non-true elsewhere. So there are lots of parameters in the unimodal family which are very interesting and not hyperbolic, and there for B different than 0, all hell breaks loose, and there are lots of things happening, and the bifurcations that you see in dimension 1 are very different from the ones you see in dimension 2, and blah, blah, blah. Okay, so this hyperbolic story is nice, but it's certainly not the case that it goes on for B very small for all parameters. Okay. So what did I say here? Yeah, right, so I said that. Right, so if it's a hyperbolic unimodal map, then it's okay. So the pruning from conjecture is true in its strongest possible version. Okay, the version 1. So right, so this is not anything to do with the Henon family, but so pruning was used in a different sort of corner of this story of two-dimensional dynamics to prove a version. So these pruning regions that I mentioned in the beginning, we construct isotopies we construct them by hand, so to speak. And Thurston has this beautiful classification theorem for surface homeomorphisms up to isotopy. And when I was doing my PhD, I started talking to Michael Handel, and he said, well, can you give a pruning proof of Thurston classification? And I said, oops, that's an interesting thing. Anyhow, so you can do that. So you can use these pruning isotopies that you can construct by hand and give a proof, an algorithmic proof, if you will, based on Handel's proof, actually, for this classification theorem, which is... And pruning also was quite sort of central in understanding sort of this forcing relation. This got to do with braid types. So so pruning was useful in sort of for other things. Now, very recently, sort of Valentin Mendoza proved some version 1 of PFC, this models version of the pruning from conjecture, for certain hyperbolic parameters which are very far away from unimodal, right? Okay, so as I said in the beginning, so if you're bumping, perturbing the unimodal family, then you can prove it for hyperbolic parameters. But he proved for hyperbolic parameters very far from unimodal space, and his proof is just a very clever, sort of observation of some we used complex techniques and some results of Arai, which are computer assisted. So Arai had some computer assisted proofs of some things, and Valentin noticed that this can be used to give a proof of the pruning from conjecture for certain parameter values. And so he was able to check in particular that some error preserving maps, Hanon maps, are conjugate to some pruning models. Okay? So the way you do it is by kind of building these paths in complex parameter space and looking at the automorphism of the map, the return maps. Oh, right, so I wrote that there. So Valentin's method consisted of checking. He checked that the shift automorphism that appears after you go around a path in parameter space. So you start at the horseshoe parameter. So at horseshoe parameter, real horseshoe parameter, and you make a path in complex parameter space, you come back, and then there's an automorphism, and you look at this automorphism, and you check that has to do with a pruning region, and then you prove that, in fact, the pruning from conjecture is true for these parameters. And his proof, his observation is so he could prove that it was true for these parameters of Davis, Mackay, Tsunami, and for some other sets of parameters. But presumably, if somebody had enough computer time to make these rigorous computer things run for long enough, you could check for lots and lots and lots of parameters. Okay? So for parameters, but again, hyperbolic parameters. Okay. All right. So then there are results to be. So these results I was talking about here, so Valentin's results and even, these, of course, live naturally in the hyperbolic realm. And at the other extreme, you could look at infinitely renormalizable Hanon maps, which is something that Misha Lubitsch and Marco Martins and I started looking at several years ago. And we've been working at proving this version 1 of the pruning from conjecture for such maps, right? For infinitely renormalizable Hanon maps. But so worked, and things move along, and no major difficulties were found, except that at some point I ran out of stamina. But I expect to be able to come back to that and finish this proof, because it's all there, I think, right? So, and give a proof of the pruning from conjecture for some cases which are very, very far from being hyperbolic, right? And then, pruning, so also working with Phil Boylan and Toby Hall on some torus maps for rotation sets. rotation sets for torus maps, I'm sorry. So the last slide, I think I'm finishing ahead, as a matter of fact, because I've never given a beamer. Well, I have given one beamer talking about it, but I'll have to help translate for those who don't speak Portuguese.